It will help in this section if you have a isotropic vector matrix, which is a vector equilibrium with its nucleus articulated, and a two-frequency tetrahedron or an octet truss. We'll be thinking about each vertex as being the center of a sphere, how an edge goes from one sphere center to another. When you do closest packed spheres, they outline the vector equilibrium, isotropic vector matrix, and the octet truss. That's where you just continue the form out sideways. We will also focus on the nuclear ball in a planar array. So this is a plane. You can just keep drawing circles, and this remains the nucleus, and also an omnidirectional or an all directions. Here you can see a small vector equilibrium. There is a nuclear ball, but you can't see it. It's colored, and then if you just keep going, it grows just as you'd expect. But what you'll be asked to consider in this section is thinking of a nuclear ball. Center of this triangle, you can also think of it as a hexagon. And then that is a nuclear ball as you go omnidirectionally. So in this model that I'm holding, I made it a nuclear ball in a tetrahedral expansion. But you'll be thinking in this section about nuclear ball always expanding this way in the isotropic vector matrix style. Next, when considering that nucleus, as you can see the center ball of a isotropic vector matrix, you'll be asked to consider how it's constructed of tetrahedra. So here is the shell without the center, and then you can see every triangular face is actually a tetrahedron leading to the center. And you'll be asked to think about these tetrahedra. Each of these have 6 edges, because a tetrahedron, of course, get your model in hand, it has 6 edges, 1, 2, 3, 4, 5, 6. And they agglomerate to form the isotropic vector matrix. So the isotropic vector matrix is composed of tetrahedra. We now read section 421. Function of nucleus in isotropic vector matrix. 421.1. Because the spacing of absolutely compacted spheres is tangential and hexagonal in great circle cross-section around any one sphere, the contact points are always spaced equidistant from the centers of the spheres and from their immediately neighboring points respectively. Wherefore the dimensions of a system of lines joining each and all adjacent spherical centers are identical to the universal radii of the identical spheres and therefore to each other. Such a universal system of identically dimensioned lines growing outwardly from any one nuclear vertex constitutes a universal vector system in dynamic equilibrium, for all the force lines are of equal magnitude. In the isotropic vector matrix, every vector leads from one nuclear center to another, and therefore represents the operational effect of a merging of any two or more force centers upon each other. Each vector is composed of 2 halves, each half belonging respectively to any 2 adjacent nuclear centers. Each half of the interconnecting vectors represents the radius of one of the 2 spheres tangent to one another at the vector midpoints. Unity, as represented by the internuclear vector modulus, is of necessity always of the value of 2, for it represents union of a minimum of 2 energy centers. Function of nucleus in isotropic vector matrix. Every vector has 2 ends, both of which join with other vectors, to produce both structural systems and total cosmic integrity of regeneration. Every vector unites 2 ends. Each nuclear ball can have a neutral function among the aggregates. It is a nuclear ball whether it is in a planar array or in an omnidirectional array. It has a unique function in each of the adjacent systems that it bonds. The nucleus can accommodate wave passage without disrupting the fundamental resonance of the octaves. The tetrahedron is the minimum, ergo prime, non-nucleated structural system of universe. The vector equilibrium is the minimum, ergo prime, nucleated structural system of universe. Corollary: identically dimensioned nuclear systems and layer growths occur alike relative to each other, and every absolutely compacted sphere of the isotropic vector matrix conglomerate, wherefore the integrity of the individual energy center is mathematically demonstrated to be universal both potentially and kinetically. Ideal vectorial geometry of nucleated systems. It is experientially suggested that the structural interpatterning principles apparently governing all atomic associability behaviors are characterized by triangular and tetrahedral accommodation, wherein the tetrahedron's 6 positive and 6 negative vectorial edge forces match a total of 12 universal degrees of freedom. The tetrahedron's exclusively edge-congruent agglomeratability around any one nuclear point produces the vector equilibrium. These structural pattern-governing conceptualizable principles in turn govern all eternally generative design evolution, including the complex patterning of potential, symmetrically and asymmetrically limited pulsative regenerations, only in respect to all of which are ideas conceivable. These patternings are experientially manifest in Synergetics' closed system topological hierarchy, through which we can explore the ramifications of the idealistic vectorial geometry characteristics of inherently nucleated systems and their experientially demonstrable properties. For possible relevance to the periodic table of the elements, see section 955.